chart.
Angel, yes, please.
Okay, great. So, hello everyone. Welcome to the Dreams Technical Seminar Series. To this community, Professor Frank Chang needs no introduction. As his contributions to high-speed electronics and RF technologies have translated into impactful and widely used products across the industry. So it's my pleasure to welcome him to today's Dreams Technical Seminar Series. And as you know, Professor Frank Chang is a distinguished professor and the Wintec Chair of Electrical Engineering at UCLA. He has also been a very strong supporter of the Dreams Hub and helping drive its mission forward. And we are honored to have him share his insights with us today. And please join me in welcoming Professor Frank Chang. So, Professor Frank, the floor is yours.
Thank you very much for inviting me. And thank you for giving me this opportunity to share some of the thoughts I had in the last couple of years in terms of what's the status now and what may be possible for the future for the future generation of for many years to go, what maybe the possible directions for the technology and the circuit development there. So that intrigued me to give us such a talk. Actually, I made the same talk last year in the RFIC conference. I thought the audience thought that has some certain values that I will also like to share with you in today's meeting. If you have any of the comments, critiques, or anything, that I'd be very much welcome to share. Yeah, thank you. Yeah, so the topic is the future system on chip for full spectrum utilization from RF to optics. Of course, that is a dream of all of us. Yeah. So currently, we're in the frequency or spectrum, the scaling in the middle of this millimeter wave or sub-millimeter wave the regimes. Yeah, so we can take a look on the current issues, pros and cons with such the utilization of such a spectrum for both sensing and communication applications. And let's review a little bit, understand the strengths and the weakness of the CMOS-embedded strategies and possible strategies that we are adopting for realizing the millimeter wave system on chip. To go over a few applications that may appear to taking good advantage of the CMOS switching properties and high integration the scale in terms of the implementing a system on the chip, or many different systems on the chip, and also comment on some of the multi-band interconnect. I always thought that may be useful for future the either intra or inter the chiplet or inter packages or inter the data center subsystems communications, all those. I would like to get you the attention and interest in that. Those. Then we can talk about the mainly talk about the what falls short, the technology shortcomings in terms of most important the power range and the frequency coverage. Those. Yeah. Then discuss about the a proposal I'm making, and I'm also trying very hard to implement or realize that, although it's not an easy task. Talking about the what may be utilized or the best junction for the function. We always thought about that to conduct the heterogeneous integration down to the junction at the junction level. I always thought in terms of functionality, that may be the best pathway. Yeah. Then we're talking about the a good example of that is to replace the nitride by using nitride to replace the silicon, the FinFET or CMOS drain, especially for the NMOS or n-FinFET. Then set the possibility for us to implement the RF optics to sort of integrate we call the bandgap limited devices with the transit time limited device into one. That made the set the good footage for the future development to implement RF all the way to optical full spectrum SoCs. That's what I'm calling. Yeah. Firstly, let's look at the I would call the information scaling rather than the integration scaling that we often talked about in the semiconductor integrated circuits. So the information does scale with spectrum bandwidth according to Shannon's the principle. Shannon proclaims the total data throughput capacity indicated as a C here. That is the product of the spectrum, which is a radio frequency spectrum utilized by the network, times the number of the orthogonal antennas on the uncorrelated signal path, and that times, of course, the we call the signal quality, the signal noise ratio, the logarithmic ways included into this equation. When we saw I should say the original RF engineers that we started with a few hundred kilohertz in communication, that's sitting in the low part of the so-called communication, the spectrums, from today's standard. Basically, it started from about 100 kilohertz initially, with the wavelengths is about several hundred meter, long, all the way to today's that we're at about the 100 gigahertz. Yeah. So from 100 kilohertz and to 100 gigahertz, that is about the 10 to the 6 in terms of the bandwidth availability that can provide it for the communication. Today we're talking about the millimeter wave. Then we're talking about from 30 to maybe 300 gigahertz, or 0.03 to 0.3 terahertz. Then we gradually move to the sub-millimeter wave. That is from 300 gigahertz, so 3 terahertz. But as you can see, it's very much messed. The spectrum areas is highly impact by the oxygen, the moisture content that in the air that cause we call the atmospheric opaqueness. Yeah, in a region that actually that affect the communication very much. It is not a good spectrum bandwidth for any of the sensing or communication applications. Yeah. But over the hill, gradually that we can start to see the end of the tunnel, the light in the end of the tunnel. But that have to jump the frequency all the way from a few terahertz to the visible light, for example, which is about 330 to 750 terahertz, in that range. But we're currently are limited within the millimeter wave or sub-millimeter range. Mainly the devices we're using the transit time device. Yeah, as you all know, the cutoff frequency in terms of the carrier transit in such a devices, we're talking about the distance between the source and the drain. Right now, the distance, the spacing is about around 10, 20 nanometer. So therefore, the F sub t itself is already limited. Then plus, because of the gate material, it was implemented within these devices that also caused additional problem in boost the so-called the cutoff frequency for the microwave or the Fmax. Yeah, there is a simple formula. You all know that basically the Fmax, the relationship between the Fx and Ft is about the square root of the output resistance, which is typically at about 50 ohm, let's say, divided by the gate resistance, the Rg, square root of that, and times F sub t. Unfortunately, the Rg for the modern CMOS is pretty high due to the work function requirements. So that end up, unfortunately, these CMOS devices that are not particularly good for the microwave, the power, the amplification applications, for example. And that set the limit. On the other hand, also because of the CMOS mainly is to aim for the digital switching. And so that also set the ceiling in terms of the supply voltage for such a devices that could not take more than probably 0.8, 0.9 volt for all the future, the highly scaled the FinFET, for example. So in that case, the power delivery is the issue. Now that what we already knew. And in my own opinion, that also the set the constraints for the entire millimeter wave, the commercialization. It actually it has a substantially limited there, but we can talk about in a moment. Yeah. So the scaling itself actually is equally impressive than the ones as the scaling of the integrated circuit. We're talking about when I started my career, we're like 10, 15 micron in the feature size. The most critical feature size now down to we're talking about a few nanometers, and consider they're like in the two-dimensional scale. So that times together is also the scaling. The area scaling is about also the 10 to the 6 or 10 to the 7. Okay, but fortunately, although the Morse law may be well in a two-dimensional way may be limited, but because the third dimension today that we're still able to continue.
Professor Chang, one quick question. Is the slides, are you moving the slides?
Slide is not moving?
Oh, now it is moving. It
Oh,
was
it
not
doesn't move.
moving.
Okay,
Yeah,
okay, yeah,
now
yeah.
it is moving.
Okay, sorry. Maybe I didn't go as fast as you. Okay, but anyway, so the scaling is inevitable, but how are we going to together as is a serious question. Yeah. So the pros and the cons, actually, I don't need to go too detailed about that. Yeah, the main problem, as I say, is because the air, the oxygen, the moisture content that causes a problem. Although the quasi-optical, the wavelengths give us a certain advantage in terms of antenna array or phase array, that kind of implementation. But on the other hand, the cost is rather high. The cost is rather high. You cannot imagine, to implement a communication or sensing for 100 meter, they will require the 25, 30 dBm of the power. And if you are going to implement with array, then the cost is not affordable. Yeah. So, but on the other hand, the CMOS did give us many advantages. So I would like to first just to go over the certain advantages that we never imagined initially with relatively less scalable the 3-5 compound technology, although they do offer the power delivery, the strength and efficiency. Yeah. So one good example is the transmission line implementation on the CMOS substrate, and that could be switched in and out. I'm sorry. By a digital arrangement, such as a transmission line, differential transmission line, at the virtual ground point in between, then you can sort of dissect conducting the metal bars underneath. It's separated into a different two groups. Then you use the CMOS switches to either you connect them, you engage them, or you disengage them in such a way you generate an effect. Historically, we call the artificial dielectric. Yeah, when I a few times taught the guided wave courses, I always liked the Rob Collins the book, and on the particular on the chapter 12 of this textbook, it showed and also you can find it from Jackson the electrodynamics book, the periodical structure by metal, either the rods or the strips or the points, that you can emulate these metal structures to form almost like a ceramic type, a periodical type of the structures. And such implementation in the past was not practical. So therefore, although it has a good idea about it, but in terms of practical use of it, after the Koch, W.E. Koch, invented it, and many textbooks has referred to it, its practical use is not there. But the things change when you start to use lithography, the implementation on the wafer. You can imagine the metal stacks in the modern CMOS with very finely defined the metal pieces. You can synthesize your own ceramics within silicon. So that is the point. So I would call such a structure, I give a name because the digital controlled artificial dielectric. Yeah, simply because you can build your own ceramics in there. Yeah, with such an arrangement, a few things happens. Firstly, with such a linearly building up the passive, almost the passive structure, it really shows the extremely linear phase and the frequency relationship when you start to switch with certain digital states that you can implement all these switches and implement the 4 to 16-bit, for example, the thermometer, the encoders. Now, that you can actually manage it digitally to control the dielectric constant. Yeah. And because the dielectric constant with such a slow wave structure, then not only you can vary the dielectric constant, you can boost the dielectric constant. As you can see this, it depends on the spacing between the strips or the strip itself. They can actually you can make these effective dielectric constant when you get in very fine structure become very high, 20 some times higher than the without the such a structure at all. Yeah. So it has a very wide range. So uses such the DICAT, I call digital control artificial dielectric. It can serve as a control knob for many different applications, for impedance matching, for resonance frequency, the frequency tuning, and for phase shifting. So it actually is a very ideal device because it can vary the permittivity of the transmission line by digital switching. You can vary the permittivity of the transmission line, so therefore you can build the digital to phase converter this way. Okay, if you simply try to implement the transmitter, for example, without doing the amplitude modulation, but just the phase modulation, you can get the extremely high density of the constellation states. For example, in this case, in terms of the direct frequency modulation at the carrier, in this case, I think the Tim Naraka, this PhD thesis of his, he can build a 256 squared constellation state with one degree the angular and 0.00007 magnitude resolution with such the constellation state. And at that time, he can only do it with a static, switching so quasi-static. So with the EVM, for example, less than 31. But today, actually, my student recent work indicate we can do 1024 quant at the high millimeter wave frequency around the 100 gigahertz. They say around with a very wide range. Yeah, with a simple array, just only use the phase modulation only. Yeah, so that is the advantage of the to using the DICAD digital control artificial dielectric to enabling terahertz generation, for example, on there. That's another applications. Yeah, we invented these symbols that to add into the oscillators. With that, a few stages, then you can beautifully implement the either the integer of the frequency or the fraction of the oscillators. Taking advantage of these transmission lines, basic is a true time delay type of the characteristics. So that's one of the major things that CMOS can provide. We never do that in the past. There was a more discrete 3-5 technology. Yeah. The other things is although this FMX is somehow limited in the FinFET device, but for some of the CMOS device, for example, this one with a 65 nanometer, even with that kind of dimension, we actually we demonstrate the integrate the phase lock group at the terahertz. Okay, the way to do that is to combining the third harmonic generation use this triangular type of configuration, geo configurations, and tune out the output frequency at the third harmonic, and with other manipulations down to the subsampling the process and down with the to be aligned with the input source at around the sub-gigahertz. We actually can demonstrate very, very high PLL, which can synthesize frequency at as high as 560 gigahertz. With this particular range, and these are the tested output frequency that tested. So it's locked at the terahertz tone and tested the 11.5 gigahertz to show the after the dividing stages to observe that. Yeah, and it has a 20 gigahertz locking range from 450 to 460 gigahertz in the range. And the phase noise, no surprise. Actually, it follows the rules that we typically will consider is 20 times the log of the ratio between the frequency. It pretty much follows that without any surprise. Yeah, so it's very predictable. That means even with this frequency range. And later we also implement that to form a certain arrays and trying to be able to deliver more power at the millimeter wave or sub-millimeter wave range. In this case, is a 550 gigahertz to demonstrate the coherent phase array. Yeah, as you can see, has to be very carefully implement these and buffer then with in the single-ended structure, and within the oscillator itself is a differential. Simply with that, this 2x4 differential antenna array was driven by 8 pairs of the synchronized VCO. This was demonstrated as well. Okay, and here it shows the synced 540 to 550 array radiator that was demonstrated also a few years ago. And more recently, we are also able to connect this one with the PLL I shared with you earlier, and make it actually the frequency synthesized, the phase array. Yeah, that is also demonstrated. We haven't had a chance to publish that, but I think we will in the future time. Yeah. So all these are the good things about CMOS. Yeah. The other things the CMOS has, because it's a wonderful marriage with digital electronics. Under the DARPA support, we also built the first self-diagnosis and self-healing radio. Yeah, such a healing radio on the chip with a block diagram indicated as here, mainly is trying to boost the performance yield of the transceiver with such a high frequency and very, very highly specify the performance in order to be consistent at getting these, and also has such a self-awareness capability, so they can conduct a self diagnosis and the self healing when they're in the isolated environment without any human interference there. And as you can see, in order to implement such a smart AI type of the transceiver, we're using quite a few different sensors. In the transmitter side, we have the power meters, envelope detectors, temperature sensors, and the temperature sensors at both the transmitter and the receiver. And the digital side, we're taking building we call the self-healing controller, which has a the parameter estimator, the block, okay, that to decide how to conduct we call the cautious control. Yeah. And in order to have a very fine control, the sensing capability, that we have auxiliary ADC, which has a low speed operation, but with a higher, even higher resolution of that. Then we also have a DDFS, direct digital frequency sensor, to generate the tones to check the linearity operation of both transmitter and the receiver. Yeah. So I was amazed that it was a big success. As you can see, it's a big chip. It was designed by 8 graduate students, and not even one of them could make any mistake, even slight mistake will prevent this entire integrated circuit from functioning correctly. It was a total to my amaze. It went very, very successfully, very, very accurately. That we conducted both digitally and RF-wise. In terms of reducing the processing variations by 50% with improved performance, including some the 12 dB OIM3, the suppression, the linearity. In terms of image rejection, 16 dB the suppression. All these are conducted by itself, not controlled externally. Yeah, you just turn it on. It started with the not so good performance, and gradually it self-tuned it into with a perfect performance. Yeah, by itself, simply just by itself. It's really to my amaze. Yeah. So this is a first demonstrate self-healing, and actually to any frequency radio on the chip. Probably this is the first time, and also this is maybe the only time. I have not seen any other demonstrations about the implementation of to such a scale. Yeah. So we got the envelope, the detector, the sensing the signals at the PA output, and it feeds that back to the self-healing, the controller and the receiver. So it's looped. This is a transmitter part, and it's looped back to the receiver. And back to the self-healing controller, and with that, the self adjusts the IQ phase and amplitude, in terms of offset, in terms of magnitude, in terms of everything. Yeah. for image suppression and for PA bias, also tune the current of the PA bias in order to achieve the intended OIM3 suppression. Yeah, so that was a very fun project. Yeah, I really appreciate the DARPA's this opportunity given to me. Yeah, and my group, the students. Yeah, and it produced so many successful the circuit designers for our industry, for our country. Yeah, for Northrop Grumman included. Yeah, it was a very happy ending. Yeah, with the project, with a total success. As you can see, the yield, the performance year is 100%. Yeah, and if you don't do such a self-heating with the design, the simulations that the capability we had, will end up with 0 yield, no yield. Yeah, according to this spec. Yeah, the spec will including the noise figure, the output, the bandwidth, the OIM2, OIM3, EVM, P1 dB, TX, OIM3, EVM, synthesizer phase noise, the channel frequency selection, IQ mismatch, and the ADCs, including the ENOB, the greater than the 9-bit, better be 10-bit if possible. Aggregate the performance year and the power consumption, and the burden to the power consumption is very, very low. Yeah, it's less than the 5%. Yeah, both because of the power, the controller itself and the process, all the sensors, all those, they don't consume that much power, and also plus the test period. Yeah, the self diagnosis and the self heating period it's not very long. It's a very short time. So the two factors add together, multiply together, they end up the power is actually quite low. Yeah. So yeah. The die size is about 37.6 millimeters squared. Total pads 275 pad. Yeah, and the power pads are 90 of them. Yeah, so it's not the simple circuits. Yeah, that demonstrate. So that is two things which is good. The other things we come up and thought might be useful for future communication is the interconnect. Interconnect is very important in our opinion for future, either the inter-memory and NPU, GPU, or CPU, the communication. Also is between the package and the package, for example. Yeah, it will be very important to maximize the energy efficiency or to lower the energy consumption to 0.1 picojoule per bit, right? That is the recent Department of Commerce, the goal for inter-package communication. Multi-band, the concept I originally had is I saw the continuous pushing in the time domain only the process, and that can only increase the bandwidth of the entire communication into one single band. Yeah, and if you are facing a complicated the complex the channel notch and other the system environments, you end up with a very severely distorted eyes. You know that in terms of the bit error rate, that is terrifying. Yeah. So my thought was if we can instead of using the broadband to put all the burdens on a single frequency band, instead we're using multiple band. In this case, for example, we demonstrated with 4 bands, the baseband and RF1 frequency band, RF2 frequency band, and RF3 frequency band. Okay. Or actually, in the demonstration, we only demonstrate the 3 of them. So baseband, 3 gigahertz band, and the 60 gigahertz band. Then, because in the time wise, it's more relaxed. You know, you don't need to squeeze yourself to such a tight the time constraints. Yeah, and also the overall eye-openingness is also much greater, improved. Most importantly, you don't force everything to the extreme. You operate everything in the linear region, and that basically save you the everything, not just the energy, but everything else too. Yeah, resolutions, everything. So this is the overall diagram. In the baseband, we're using the PAN4 signaling, and for the high frequency, we use 16 quant. Yeah, and this is the end up with the beautiful eye diagrams that we demonstrate. One of the keys there, people never did not detected that earlier, is during the transmission. If we don't do the metal base, the transmission, okay. Oh, actually, even we do metal base, it doesn't matter. When the signal got mixed up by the carrier, and the low pass characteristic of the LTI system, that will causing the misshape, right? Is eroding of the over the frequency band. But when it's mixed down, actually, it's self-canceled out. Yeah, of the such the effect. So the equalization could be self-equalized, yeah, with the double sideband signaling. So if we choose a double sideband of the signaling, then it could be the signal itself could be self-equalized. So that was some of the interesting findings along the way of designing such a system. Such a system also has a certain advantage of providing so-called contactless for the interconnect. For example, in this case, because you got the transmitter and the receiver, for example, rather than actually go through the space rather than any of the cables or transmission line, then you can bend it in any of the direction, vertical, offset, the side, diagonal, anything. Yeah. So with such a system, then it has a flexibility for some of the high G vibrating systems, for like missiles and other things. That could actually improve the interconnect reliability. Yeah, it only uses so-called near field coupling for all these launch. If you pay attention to your Apple Watch recently, they actually adopted this scheme. Yeah, unfortunately, this was the spun off into a commercial company. During the pandemic time, it did not work out in business, so it was sold to Molex. Yeah. I don't know what kind of business deal between the Molex or other companies with Apple. I simply just noticed such a scheme already implemented into the Apple Watch. Yeah, but I cannot say that they must have utilized our technology, but the similar technology has been adopted. Yeah, that is for sure. Yeah, and this is another case that we demonstrated using the plastic waveguide. Yeah, plastic waveguide is very interesting. If you are talking about the millimeter wave, the signal propagation in the free space transmission, for example, for 1 meter distance from the transmitter receiver, simply just calculate with the wavelengths within this millimeter wave or some millimeter wave range. Let's say 150 gigahertz. Then your attenuation in the free space is about 40 to 45 dB for 1 meter. Okay. And if you use if you just using the baseband only, you lose about the same dBs, 35, 40 dBs. If you're using the metal cables, for today's the multiplex or demultiplex SerDes system, that was exactly the same case. But instead, if you don't use the free space, you don't use the metal, but use the waveguide, the plastic waveguide, especially the hollow plastic waveguide, the tube, we call the RF pipe. Okay, if you use that, then the loss of the energy about 1 dB per meter. Okay, So I think for the future inter-packaging communication, this is maybe the way to go. Yeah. And here, let me show you the one of the customer, LG, which had actually bought the transceivers licensed from our technology, and they build their panels. Yeah. Within minutes, you can build the entire channel. Of course, then you can also use for other things like phones and other displays, especially for building panels, actually. Yeah. Without the cable. Yeah, simply you're using the multi-band RF interconnect. Yeah, that's a good example. And this one I want to see you. Just say, want you to see. This is a company in China adopted our technology. Yeah, they build a panel on the building for in Shanghai and other cities. Yeah, see, this is the power. This is the magic of the RF interconnect. Okay, yeah, yeah, it's kind of fun to see that. Yeah. Other things CMOS can also do with the help of the 3-phi. One good example is a passive imagers, yeah, that we use. With the indium phosphide front end, we're able to, without using any 2,6 compound or any small bandgap material, using the CMOS, the base end, the baseband and the front end, the indium phosphide, we can get a passive detector, yeah. We can find the emissions out of your body. We can see that actually. Yeah. So that is, yeah. And also we using the Armstrong, the oscillator front end. You know, we call it the Armstrong called the regenerative receiver, that we use that and use a few of them to interfere with each other, you know, with intermixing of the frequencies, then we can do multicolor and multiband. Yeah. So CMOS is also be very powerful. Actually, we find out together with the jet proportional laboratory with my former student Adrian Tan, we're able to build the single chip, the baseband processor, you know, for the rotational, the chemical, the microscopic, the sensing, yeah, sensors that has been built in for many the space missions so far, all very successful. And as long as I know, this is the only single band, yeah, the baseband processors that have been implemented. With all the good things about the silicon, one thing apparently is missing in the series. Let me explain why. If you look into the future and see what can be done if we along the pathway of the 5G, 6G to NG, let's say, into the future. More you think about it, on the vertical axis, you look at the coverage, the power efficiency, the spectrum efficiency, their relationship. And in terms of horizontal, if the frequency space, you look at the spectrum efficiency. More you see the spectrum efficiency into the future is less important than power efficiency, because we do have, once we increase the keep on moving up in the frequency, but reducing the wavelengths, increasing in the frequency, then the spectrum efficiency is less important, and actually more important is the power. You know, without the power, you cannot achieve so-called a new coverage area like a sky, sea, space. These requires extreme coverage. You just cannot do that if you don't have a power efficiency. So overall, the conclusion into the future, actually the coverage is the key. Yeah, that probably is the Elon Musk, on Elon Musk's mind, that's probably most important, is the coverage. It's not the spectral efficiency anymore, perhaps, yeah, for a while at least, yeah. So that reminds a old story, since also my old colleague Peter Esbeck is also here. remember the HBT has transformed, basically transformed the brick phone to a smartphone from the left to the right. If you open any of the iPhones today, this is an example of the iPhone 14. You can see all these color framed parts, other than these big, gigantic, the silicon, the SoCs, the Qualcomm and the others. Actually, many of these, for example, I only marked the Skyworks part of that. 1, 2, 3, 4, 5, 6, at least 3 of them. And this is just one side of one side of panel. The other side of the phone, probably you will see the Avago, the Broadcom, and other companies. So many of the III-Vs into the cell phones are more than you can imagine. Okay, more than you can imagine. I just using the iPhone 14 as an example. So actually, without the HBT, you cannot imagine how today's the phones can be commercialized to such a popularity. It's just not possible. So it is very important to have an efficient way that you can deliver the energy and to across the vast the distance for connectivity. Yeah. So the same thing you will think, what limited today's millimeter wave. The same thing. There is no the cost effective and energy effective the silicon solutions for it. So that pretty much limited. The only possibility, if you look around today, unfortunately, the III-V HBT either it doesn't reach to such a high frequency, or its cost is also high. One popular solution, maybe in the future, is a nitride with such a characteristics that it has a high breakdown field or also high mobility. Yeah, for example, and good enough thermal conductivity or equally good. Yeah. Recently, that we have tried to implement the methodology we call the V-groove, the etching to expose the silicon's 111 surface here. Okay, and that happened to be lattice match to the gallium nitride, aluminum gallium nitride actually more closely. Then gradually that we can transition to a gallium nitride, and with continuous growth of that, when the both sides started with a hexagonal structure, when they merge it into the center, then they become a cubic structure. So that has been, we have proved that. Yeah. So we imagine such a device, such a growth process could be implemented in the field effect transistor type to replace the silicon drain with a nitride. Because the silicon technology has such a wonderful gate process of what's channeling everything. The only thing missing actually is the drain breakdown. So that's what our original thought, and we demonstrate such a feasibility, and we got the patent all around the world. Yeah, U.S., Japan, Germany, China, South Korea, Taiwan. Yeah. So we believe that is a good possibility there to perform what's called the bed junction for the function there. Yeah, yeah. The idea is even we can improve the VDS, the breakdown, drain source breakdown from 1 volt to 5 volt, as you can see. Then the P1 dB can increase from a few dBm to 30 dBm, and the PAE increase from single-digit number to quite a significant amount. This is all possible. Even on top of that, if you look at the recent publications, the full spectrum in the visible lighting areas, the blue, the green, the orange, the red, they actually could be all implemented with the nitride. You don't need anything else. You only need to change to vary the indium content of the nitride. Okay, so That intrigues the thought we have. Maybe on top of these drain, instead of just leave it as a drain, we can actually build the photonics device, the both transmitter and the receivers the same, with a multiple quantum well on top of the drain, and implement it with such a device to merge a bandgap limited device with along with transit time limited device into one device. Okay, that will help us overcome the barrier of the sub-millimeter wave into the future, either long wavelengths, the infrared, or eventually into the visible light. Yeah. With that, I think that probably then the true time for the optical interconnect on chip, that will happen with the perfect alignment that without bothering the hand alignment or anything. They're perfectly aligned they're within the accuracy of the photolithography. Yeah, modern photolithography. Yeah. Or you can build the LiDAR on the chip, similar way. But most important, I think, is for the optical based, the on-chip interconnect, which, as I mentioned, the interconnect is so important for many, many reasons today. And that can help us continue the bandwidth scaling from RF to optics. Yeah. So to summarize my talk, a few points for your takeaway. I think number one, I think the future radio radar photonic system that demands even higher bandwidth resolution and the superior performance cost effectiveness integrated system solution that can be enabled by hetero integration at the junction level. Yeah, I remember the late professor Herr Kromer. That's he already said. The button is more important, and the junction level integration, heterojunction integration is always the key into the future. I certainly agree with that. Cannot be more. Yeah. The second thing is the superscale CMOS. It excels the baseband SoC implementation, but falls short in delivering high drivability and the linearity or efficiency cost effectively. I think that is very key. You must be cost effective. I think the entire problem of 5G, 6G communication today, which prevented from the further commercialization, is that there is no good solution for power amplification. Because for microwave power amplification, HBT served the job, and at that time you put a discrete or a semi-discrete HBT outside the CMOS. It's not so much a problem because the energy loss along the pathway is a quarter dB or half a dB. It's no big deal. But today, when the frequency goes high, no matter how well you package, if you want to bring the PA and externally, you're going to pay the price, a few dB price. Not only that, if you want to implement it in the phase array means, it's just simply not easily can be cost effective. And the last thing I think most important, the spectrum scaling will continue. We cannot just sit here and expect our next generation to still work on the millimeter wave. Yeah, they'll be beyond us. Yeah. So the header integrating 3.5 material on CMOS drain, I think that holds the greatest promise to boost system operation range and fulfill the future sensing communication needs from RF to optics in bandwidth, range, resolution, manufacturing, and the cost challenge. Yeah, that's the only way to face that. Yeah, with that, I thank you for your attention. Yeah, for the patience for the talk. Thank you. Thank you very much. Yeah.
Thank you, Professor Chang, with an
Yeah.
exciting talk. I mean, especially all these some of this.
Yeah.
Some of this novel futuristic research, especially on this heterointegrating trinitride material on the CMOS. I mean, those are something very exciting. We have time for a few questions here. Before So let me check if there are any questions here in the chat. There is no questions, but if anyone has any questions, please do ask.
Frank, and there's
Peter.
one comment. This is just amazing. So many creative ideas and innovations that guide folks in different directions. One of the things that comes to mind for the power amplifiers is from your Helix program.
Yeah.
An effort. Do you think that you could cure behaviors, responses to VSWR variations? And power amplifiers have lots of problems that require sort of control. I don't know if you think that would be a good approach as well.
Thank you, Peter. Yeah, of course, you're right. There's many the important the key volumes that you can push and get the amplify the performance to further improve. In our demonstration, unfortunately, we can only also because the complexity of the control itself, we thought that the easiest way is to change the current bias. So that was the only thing conducted. so it's still we're on the very simple-minded side. Yeah. Yeah. If in the future we have more chances to do so-called AI-based PA design, definitely that we'd love to work with you and others to think at how to implement that more effectively in better ways. Yeah. Yeah. Thank you.
Thanks.
Yeah.
Any other questions? Okay, it seems there is no more questions. So let me quickly highlight the technical seminar series. If you go to this barcode, you will be able to find the future seminars. The next week, February 14th, we will have Bobby Brar from Teledyne, who will be giving us the technical seminar. So we are all excited to, we are looking forward to that presentation as well. Thank you all for attending.
Thank you. Yeah. Thank you for listening. Yeah.
Thank you, Professor Chang, once again.
Yeah. Bye-bye, everyone.
Bye-bye.
Thank you so much.